mathematical work of Maryam Mirzakhani by McMullen.
Thank you so much. Well, it's a real honor to be able to speak to you on the work of Maryam Mirzakhani. Maryam has been awarded the Fields Medal for her outstanding work on the geometry and dynamics of Riemann surfaces and their moduli spaces. And among her many accomplishments and contributions, I've chosen three to give you the flavor of her work. So I'll discuss her work on simple loops on a Riemann surface, her work on complex geodesics in moduli space, and her work on earthquakes. But before I do that, I think I need to introduce you to the setting, Riemann surfaces and their moduli spaces. So we will be mostly concerned today with closed complex manifolds of dimension 1, which are topologically surfaces with a finite number of handles. The number of handles G will be greater than or equal to 2. And that means that the universal cover of these Riemann surfaces are always isomorphic to the unit disk. And from the unit disk, a Riemann surface inherits a hyperbolic metric. So the complex structure determines naturally a metric of constant negative curvature. So these Riemann surfaces come to us as objects with dual natures. They're holomorphic objects and they're geometric objects. And of equal importance will be the moduli space of all Riemann surfaces of a fixed genus. This records all of the different possible shapes for a surface of a fixed topological type, that is with a given number of handles. And by different shapes, I just mean we consider two Riemann surfaces to be the same if there's a holomorphic isomorphism between them. But any such isomorphism is automatically a hyperbolic isometry. And so the hyperbolic shapes can also be thought of as the form that's being parameterized by this moduli space. Now, moduli space has two personalities. It is a complex variety of dimension 3G minus 3. This was known already to Riemann, and in modern times, explicit descriptions of these moduli spaces as varieties in projective space have been constructed. But it also has the structure of a symplectic orbifold. That is, it carries a symplectic form which is in some sense independent of the complex structure. So let me tell you where these two personalities come from. So first, the hyperbolic geometry of the underlying Riemann surface at a point in moduli space determines the symplectic structure. In fact, if you want to describe a Riemann surface of genus 2, you can do so by describing the hyperbolic lengths of three curves, shown in red here, which cut the surface into a pair of pants. And the only additional information you need to describe the surface completely is twist parameters, which tell you how to glue the cuffs of the pairs of pants back together to get a closed surface. And these parameters, which were introduced by Fenchel and Nielsen, are called length and twist parameters. And if you form the obvious 2 form built out of these dual parameters, you get a natural symplectic form on moduli space. Now, if you don't know what a symplectic form is, let me tell you what its key use will be. If you take a suitable power of this form, it gives you a natural volume element of moduli space. And then you can calculate the total volume of the space of all Riemann surfaces of genus G. And this is some interesting and exotic number. Now, what about the complex structure on moduli space? Well, this is inherited, of course, from the complex structure on X. And in fact, the cotangent space to moduli space at a given point is naturally identified with the space of holomorphic quadratic differentials on X. So these Q of Z times dz squared, that's a vector space of dimension 3G minus 3 on any compact Riemann surface. And even better, from this complex structure and this model for the cotangent space, you get a natural metric on moduli space, a way to measure distances. And how does that come about? Well, the length of a cotangent vector, it's a quadratic differential, can be obtained by just integrating its absolute value over x. And this gives you, without any choice of metric, a number attached to a cotangent vector. So that's the metric that's called the Teichmüller metric on x, and it turns out that it's also agrees with what's called the Kobayashi metric, which can be defined for general complex manifolds. Okay, so that's the background, and let me tell you what moduli space looks like, because people work with moduli space all the time, and we all have our independent images of it. Here's what it looks like to me. So first, moduli space is the quotient of a bounded domain in Cn by the action of a discrete group, the mapping class group of a Riemann surface of genus G. The mapping class group is an element of low-dimensional topology. So low-dimensional topology is naturally wrapped up in the theory of moduli space. So here's my rough picture of what this Teichmüller space looks like. We take the quotient by the action of the mapping class group, and we get moduli space. So moduli space, in my mind, is a very rough object, which looks somewhat like the surface of the Earth, except it's not compact. It has an end which goes off to infinity, the little tail that I've drawn in this picture. And the reason I say it's like the physical Earth, rather than just a sphere, is that it has the following very odd property. First, the symmetry group of the universal cover is in fact simply this mapping class group, mod G. It's a discrete group. That means the universal cover is a completely inhomogeneous space. It has no continuous automorphisms. And even more striking, if you take 2 points on moduli space, if they are isometric in a small neighborhood, in fact, if just the cotangent spaces at those 2 points are isometric, then in fact the 2 points have to be the same. The 2 Riemann surfaces are the same. So it's as if you're on the Earth and you look at a small area around you and you can tell that you're in the middle of the Pacific Ocean as opposed to Rio, just by observing this small neighborhood. So moduli space is totally inhomogeneous. And in this way, it's very different from the spaces that have been classically discussed in differential geometry. It's not like a sphere, it's not like hyperbolic space, it's not like the quotient of a Lie group by a lattice in a maximal compact group. It's not a locally homogeneous space. Nevertheless, many of the properties that have been established via analysis on these symmetric spaces or the homogeneous spaces turn out to hold for moduli space. And that's one of the themes I'd like to develop. But first, let me turn to a simpler kind of question. This will be my first result of Mirzakhani that I'd like to discuss. This will be a theorem that concerns not moduli space, but just one Riemann surface. Okay, so the problem is, count the number of simple closed geodesics, simple loops, on a fixed Riemann surface of length less than or equal to L. Now let me compare this first to a classical problem. Most loops on a Riemann surface cross each other. And classically, one counts the number of all closed loops of length less than or equal to L. It grows exponentially fast. In fact, it's asymptotic to e to the L over L. This is sometimes called the prime number theorem for closed geodesics, because if you were to think of a prime, P, as a loop of length log P, then the number of primes of length less than or equal to L would obey exactly the same law. What happens for simple loops? It's very hard for a loop on a Riemann surface to not cross itself. There are many fewer simple loops. And what Mirzakhani proved in 2004 is that the number of simple loops on X grows not exponentially, but it grows like a polynomial. In fact, it's asymptotic to a constant depending on X times the length to the 6g minus 6. Now, what's very odd about this formula is not that there's a polynomial here and an exponential there. What's very strange is that the constant depends on X. The growth rate is not universal as it is for closed curves. It depends in a subtle way on the geometry of the Riemann surface in question. And although this is a theorem about one Riemann surface, to prove it, Maryam had to analyze all Riemann surfaces at once. That is, she had to integrate over moduli space, and she had to perform a delicate hyperbolic dissection as she did. And why do I bring out these details of the proof? It's because by investigating this very natural and naive question about one Riemann surface, Maryam was led to a cascade of unexpected new results. And let me just mention two of them. So first, she gave a new proof of the Witten conjecture. So Witten, in the 1990s, gave an interesting, complicated formula for certain intersection numbers on moduli space. I've written it down as an integral of Chern classes. If you take these integers and put them together, they should give former solutions to some sort of differential equations. And this was verified by Kontsevich in 1992. Witten's original proof of this and the intuition behind it is string theory. And there's still no rigorous mathematical justification of this intuition. What Mirzakhani was able to do was show that this formula flows forth naturally when one starts with a simple geometric problem concerning simple curves on a Riemann surface. So it emerges from an almost classical geometric discussion. A second kind of result that cascaded from Mirzakhani's work on simple curves is there's some universal topological statistics that can be computed explicitly. For example, suppose you draw a random simple loop on a surface of genus 2. It might cut the surface into two pieces, as shown, or it might not. It turns out the probability that it cuts it into two pieces is 1/7, and that all similar statistics can be computed by an intricate but explicit recursive procedure. Well, underlying both of these kinds of results is Mirzakhani's volume formula. And what she computed was the volume of moduli space, but not for closed Riemann surfaces, for Riemann surfaces with geodesic boundary. So there's some holes in the Riemann surfaces, which are bounded by geodesics of length L, 1 up to Ln, if there are n holes. You can still integrate the symplectic form over this moduli space, and it turns out, this is Mirzakhani's theorem, one gets in this way a polynomial in L with coefficients involving rational numbers and powers of pi. So for example, for a torus with one boundary component, the polynomial is given here, 1/24 times L squared plus 4 pi squared. And then previously only the volumes of the closed moduli spaces, that is the ones with cusps instead of boundary, were known. That's the constant term in these polynomials. And the higher order coefficients yield these topological statistics and the characteristic numbers that I mentioned. So this is the first result of Mirzakhani I want to relate. It lies on the symplectic side of moduli space. Now let's turn to the complex side. So on the complex side, I want to state a result about complex geodesics in moduli space. But before I do that, first let me remind you what a real geodesic is. So in moduli space, we have a metric. We have a notion of a straight line, that is a path of minimal length. We can look at an infinite geodesic and ask what it does. And an infinite geodesic is described by an isometry from the real line into moduli space. And if we're interested in its dynamical behavior, we could ask, for example, does it go everywhere? What is the closure of the geodesic all of moduli space? And the answer turns out to be yes most of the time. But before we get to that, there's a special feature of moduli space, which is that in addition to having real geodesics, it also has complex geodesics. What is a complex geodesic? It's similarly an isometry from a space into MG, but now the domain of the map is not the real line, it's the hyperbolic plane, and the map is required to be a holomorphic isometry from the hyperbolic metric into moduli space. And amazingly, moduli space is filled with these complex geodesics. That's a kind of a special feature of moduli space, if you give me a point and a complex direction, there exists a isometrically immersed hyperbolic plane in that direction. These are called Teichmüller disks. And Maryam's result will concern the behavior of these complex geodesics. This is like the geodesic flow in complex time. Okay, now what's the result? So let me first tell you what happens for a real geodesic. If you take a closure of a real geodesic in moduli space, it's almost always the whole space. This is tantamount to saying the geodesic flow is topologically transitive. In fact, it's ergodic and so on. And as Etienne Gis explained in his beautiful introduction to Avila's work, classically in dynamics, we are content to understand what happens almost all of the time. But what if we wanted to know, in fact, is this what happens for every geodesic in moduli space? And if not, what do the odd pathological examples, even if they're of measure 0, what do they look like? And it turns out that sometimes the closure of a real geodesic can be a sort of fractal cobweb. It's very hard to say what kinds of shapes arise, and they're certainly not manifold. There are uncountably many such possibilities. Here's two pictures of them, one impressionistic, one realistic. In any case, that's what happens for real geodesics. Okay, now let's turn to complex geodesics. What happens if we take the closure of a complex geodesic? Can we somehow, sometimes, get a two-dimensional cobweb? And this is a remarkably ambitious question to ask, because we're not interested in what happens almost all the time. We want to analyze the behavior of every single complex geodesic. We want to go beyond Smale and Tom and Paulus, et cetera, to a new realm of rigidity, which carries names like Margulis and Ratner behind it. And the amazing theorem is that, in fact, there's a beautiful description of what the closures of these complex geodesics look like. Are they fractal cobwebs? No, they are always algebraic subvarieties of moduli space. So this is the major theorem about the complex geometry of moduli space I want to relate to you, and it's actually a theorem in dynamics. So to explain its dynamical aspect, let me remark that in genus 2, we have a pretty good idea of what these varieties can be. They might be an algebraic curve, a Hilbert modular surface, or the whole space, which is a three-dimensional algebraic variety. In higher dimensions, it's still very interesting to try to figure out what these algebraic varieties are, but the miracle is that rather than being some exotic object, they're one of countably many subvarieties defined by algebraic equations. Okay, so I want to try to unfold the proof for you because there's some deeper mathematics hidden in it, but it's not really inaccessible. And it works in the following way. Moduli space itself, I emphasized, is very inhomogeneous. It's static. It doesn't have any action to it. There's nothing moving around. But if you pass to the bundle, the vector bundle, which over each Riemann surface has the vector space of holomorphic quadratic differentials on that Riemann surface, this is the cotangent bundle of moduli space, that bundle carries a natural action of the group of 2 by 2 matrices, SL2R, of determinant 1. And these complex geodesics we're talking about are nothing more than the projections from QMG back down to MG of the orbits of the action of this three-dimensional group. Now, how does SL2R act on this bundle? It's actually very, very simple. So let me ask you this. How can I tell you what a Riemann surface is? Well, one way is to just give you a polygon in the plane and tell you how to identify opposite sides, glue it together to make, in this case, a surface of genus 2. How do I give you a quadratic differential? on that Riemann surface? Well, the Riemann surface itself is the polygon glued up. If my gluings are by translations, then they preserve the quadratic differential dz squared on the plane. And so that differential, which is tantamount to saying the Euclidean metric, descends to give a holomorphic quadratic differential on the quotient Riemann surface. In fact, every Riemann surface plus quadratic differential can be presented by such a polygon. Okay, now how can SL2R act on the space of such pairs? We simply take the polygon, which is sitting in the complex plane. We think of that as the two-dimensional real plane. We apply a matrix to it, and it stretches the polygon linearly. But parallel sides remain parallel. So we can perform the same gluing operations after distortion as we could before. We can then take the differential dz squared on the plane and let it descend to the quotient, and that gives the image of this Riemann surface and quadratic differential under that 2x2 matrix. So it's a very geometric and almost completely naive process. So in terms of this action of SL2R, I can now state one of the deepest theorems that I'm going to mention today, namely the steps in the proof that the closure of a complex geodesic is an algebraic variety. And the first step is a huge breakthrough by Eskin and Mirzakhani, which describes not orbit closures, but the ergodic SL2R invariant measures on the bundle of quadratic differentials. So this is a sort of statistical description of the orbits of SL2R, and it's not a description of most of these measures. It's a complete classification of them. And every such measure turns out to come from a very special kind of analytic subvariety in the bundle of quadratic differentials. Going further, in joint work with Mohammadi, Eskin and Mirzakhani showed that all the SL2R orbit closures come from these special subvarieties. And then finally, Philippe showed that if you have one of these special subvarieties, which was a priori analytic, it's actually an algebraic subvariety. And finally, the closure of the complex geodesic is the projection of this special algebraic subvariety, so it's also a subvariety in its own right. And that's a sketch of the proof. Why is this result so remarkable? Here's the way I like to think about it. There's been a tremendous amount of research on homogeneous spaces. What's the setting for this research? It's the theory of Lie groups. We start with a Lie group, a lattice in the Lie group, a closed subgroup of the Lie group. Then the closed subgroup U acts by left multiplication on the quotient G mod gamma. And Margulis, Ratner, et cetera, developed many deep theorems about this kind of action. But this is basically linear algebra. You can think of everything here as a matrix. What did Mirzakhani and her co-workers investigate? They investigated moduli space, or rather the bundle over it, which can be thought of as the quotient of a certain bundle over Teichmuller space by the action of a discrete group. But this Teichmuller space is nothing like a Lie group, and the quotient is in no way homogeneous. Nevertheless, there's an action of the group SL2R, which plays the role of U, in the second picture as well. And the miracle is that in this totally inhomogeneous setting, there are results which mimic some of the deepest results in the homogeneous setting. So one of the deepest results in the homogeneous setting would say that if U is equal to SL2R, then the closure of an orbit is always just equal to the exact orbit of some larger subgroup of G. In other words, all the orbit closures are geometric. They come from submanifolds of G mod gamma. And what Mirzakhani and her co-workers showed is exactly the same thing is true in the setting of dynamics over moduli space. So summing up, the rich theory of homogeneous dynamics resonates in the highly inhomogeneous world of moduli spaces. And this is really a new mathematical era that is opening up here, where we're seeing that we were limiting ourselves by thinking about just Lie groups, and that some very natural geometric group actions display the same remarkable rigidity and are amenable to a complete analysis in a way that was totally unexpected from the previous ideas in dynamical systems. Well, let me quickly conclude with a third result of Mirzakhani concerning earthquakes. So here's a classical idea. If you have a Riemann surface, you can deform it by cutting it open on a hyperbolic geodesic, twisting it, and re-gluing it. And more generally, Thurston defined an earthquake where instead of cutting open along a single closed geodesic, you open along what's called a geodesic lamination with a transverse invariant measure. And in both cases, you can visualize what's happening if you lived on the surface as suddenly these fault lines develop and the sides of the surface move, they slip relative to one another, so your fence no longer joins up. The river gets a kink in it. And that's a sort of intuitive way of understanding these earthquake deformations, which are a very natural way to approach the theory of deforming Riemann surfaces. This whole picture fits into the symplectic side of moduli space. In fact, if you don't want to think in this geometric way, a la Thurston, you can simply say that you can take the function which gives you the length of a lamination on a Riemann surface. You have a symplectic form on moduli space. A function plus a symplectic form give a Hamiltonian flow. And the earthquake flows are the Hamiltonian flows associated to these geodesic length functions. Here is Mirzakhani's result. You put all of these possible earthquake directions together by taking pairs consisting of a Riemann surface plus a lamination along which to twist, and then you have an earthquake flow defined on this bundle over moduli space. And her theorem is this earthquake flow is ergodic and mixing. In particular, what this says is that if you take a randomly chosen surface and you start twisting it in a randomly chosen direction, it takes on every other possible shape of the same genus, at least with a small error. And just to give you an idea of the power of this result, previously there was not even one dense earthquake path that had been constructed or been shown to exist. But I think the main reason I want to bring up this as my final result is that it illustrates a kind of thinking that I think is very novel and is very characteristic of Mirzakhani's research. Namely, I've been discussing moduli space as if it has these two different personalities that are battling for control of moduli space. And what Mirzakhani did to prove this result is she found a bridge between these two personalities, between these two sides of the picture. On the one hand, we have the earthquake flow in the symplectic geometry of moduli space, which looks very hard to understand. It looked completely impenetrable until Mirzakhani's work. On the other hand, on the complex side, we have the action of SL2R. This is much easier to understand. And for example, it was known that the horocycle flow coming from upper triangular matrices acts ergodically and mixing on the space of quadratic differentials in the complex world. What Mirzakhani did is she constructed a measurable isomorphism between these two dynamical systems. She constructed a bridge from one side to the other, and then you can take whatever somebody had proved on one side of the bridge, carry it over to the other side, and call it your own theorem. So that's the kind of thinking that I think was completely unexpected and is bound to lead to many new results and many new ways of looking at moduli spaces. And so let me conclude by showing you a picture of what the space of laminations looks like. This is one of the pictures that one might have in mind when studying moduli space in the spirit that Mirzakhani does. It was drawn by David Dumas. And what I hope to have conveyed in this brief presentation is the way that Mirzakhani's research integrates with great originality a broad range of mathematical disciplines, ranging from algebraic geometry to ergodic theory, to Lie groups, to low-dimensional topology, and to random processes. Her breakthroughs have transformed the way we look at moduli spaces and they've led the way to new frontiers where unexpected developments are still currently unfolding. So please join me in congratulating her.